Hello, good morning. Welcome to this next lecture on complex variables and contour integrations. In the last class we left off while defining an open set. Okay, so we will continue over there. A set is open if it contains none of its boundary points. This is where we had left off last time. Okay. Another definition is a set is open if, okay, this is the double if, that is if and only if and only if and only if every point is an interior point, Okay, so if one wants to look at this, suppose this is the boundary of S, okay, and this is my set S. Now every point is an interior point, that means it has a neighborhood where all the points belong to S. So however close I get close to the boundary, I will find a smaller and smaller and smaller neighborhood of my point where all the points belong to S. So that never ends. Okay, I can move closer and closer and closer to the boundary, and I will always find a smaller and smaller and smaller neighborhood of Z0 where all the points still belong to S. Such a set is called an open set. Okay. Now a set is called a closed set. A set is called a closed set, or a set is closed. A set is closed if it contains all its boundary points. Okay, so if I write magnitude of Z minus Z0 less than epsilon, then this is an open set. Okay, but if I write magnitude of Z minus Z0 less than equal to epsilon, then that's a closed set. That's a closed set. Okay. Further, on sets, okay, an open set S is connected, okay, it's an open connected set if each pair of points Z1 and Z2, if each pair of points Z1 and Z2 in it can be joined by a polygonal line, consisting of a finite number of line segments joined end to end that lies entirely in S. Okay. So what is this situation? We have this set over here. Let's say I have this set. Okay. The set is between these two lines. It's the annular region. Okay. None of the boundary points are included. It's an open set. Okay. Now I have a point Z1 over here and I have point Z2 over here. Okay. Now these can be connected through a finite number of line segments joined end to end in so many ways. Okay. But the entire joined group of line segments, they still lie within the set S. So this is a connected set. Okay. So next, an open connected set is called a domain. This is another important definition. Okay. An open connected set is called a domain. We will be using the domain quite frequently. Okay. Further, the domain, a domain, it means an open connected set. A domain can be simply connected, a simply connected domain, or multiply connected. Multiply connected. So you can have a simply connected domain. So first of all, it is a domain. It's an open set. So here let this be a set which is an open set, boundaries not included. Okay. And this is a connected set. Now here, as we did before, we took an annular region. Okay. This region between these two lines, that is also an open connected set. But now, so both are domains, but one domain is simply connected, the other domain is multiply connected. Okay. So what is a simply connected domain? A simply connected domain is a domain such that every simple closed contour, okay, within it encloses encloses only points of the domain, okay, of the domain. Okay. So let us see here. Every simple closed contour. So in this set, I take a simple closed contour, I take another simple closed contour, I take another simple closed contour, any number of I take, there are points inside, okay, and those points still belong to this domain D, okay, they still belong to this domain D, okay. So such a domain is called a simply connected domain. Whereas think of this, if I consider a simple closed contour of this form, then all the points inside belong to D, but if I take this simple closed contour which is still going through all the points belonging to D, but that simple closed contour does not include all the points within it do not belong to D. So there is this region that is excluded from D, okay. So such a domain is called multiply connected. So the flip side is, if a domain is not simply connected, a domain is not simply connected, it is multiply connected. It is multiply connected. Multiply connected. Okay. Then last, okay, the last. A set is bounded. A set is bounded. Set consists of points in the complex plane, or the set is bounded if every point of this set S lies inside some circle, okay. What is that circle? Magnitude of Z is equal to R, okay. Else, if this is not true, okay, R is a finite number. If this is not true, the set is unbounded. Set is unbounded. Set is unbounded. Okay. So this more or less gives us a set of definitions with which we can work and move forward. Okay. Now I said I was going to give a engineering sort of hand waving sort of treatment, for one should be familiar in a proper way with the theorems of complex variables. Okay. So I will go through some theorems in a sketchy manner. Okay. So we need these theorems, so I will go through them in a semi-rigorous manner. For a rigorous treatment, you have to go through a proper course in complex variables. Okay. So theorem 1, here is theorem 1. Suppose that a function f of z is continuous on a domain, here your domain comes on a domain, okay, D, either simply connected or multiply connected, a domain D. Then if any one of the following statements, any one of the following statements is true, if any one of the following statements is true, then all the other statements are true. Okay. So, we will be given a 2 or 3 statements. Okay. When will any of the statements be true, that will not be told to us. However, if any one of them you suddenly happen to find true with respect to a particular function, then the other statements are also true. Okay. So, what are these statements? These statements are f of z has an antiderivative in D. F of z has an antiderivative in D, that is one statement. Okay. The second statement is the integrals of f of z along contours lying entirely in D and extending from any fixed point z1 to any fixed point z2, all have the same value, all have the same value. All have the same value. Okay. This is second statement. Then third statement. Third statement is integrals of f of z around closed contours lying entirely in D, all have 0 value, all have 0 value. Okay, so interesting set of statements. Okay, one is f of z has an antiderivative, which means there is a function f of z in that domain such that f dash of z is equal to f of z. This is the meaning of antiderivative. So this there is an antiderivative, which is also equivalent to saying that if I have a point z1 and I have another point z2 and I integrate f of z along a contour and I do it along a different contour, on every contour I get the same value. Whatever contour I take between z1 and z2, this integral has the same value, z1 to z2 f of z dz has the same value. And lastly, in the domain, if I start at some point and go around and come back to the same point, okay, I integrate over a closed contour. Okay, this contour lies entirely in D. F of z is now 0. This value is now 0. Okay. So in the spirit of the course, we will see some statements, proof of some statements, and the others we will accept them as they are. So the proof. So the proof of this. Okay. So how do we go about? Let 1 be true. Let the statement 1 be true. Let statement 1 be true. Okay. What does that mean? F of z has an antiderivative, f, capital F of z, okay, in D, in the domain D. Okay. Further, we have to integrate around particular contours. So let z of t parameterized in terms of t be a contour, a simple contour C. Okay. Let me change the page. Okay. Simple contour C going from z1 to z2, and t is parameterized, t extends between, t is a real number, real variable extending between a and b. Okay. So now what? Let us look at this. D by dt of the antiderivative, okay, along this curve is equal to, from the chain rule, f dash with respect to the argument and the derivative z dash of t, derivative of the argument. Okay. Now what is this? This is our function f of z, okay, which has the antiderivative. So now that is equal to f of z of t, z dash of t. Okay. We had started off by saying that f of z has an antiderivative. So this is the antiderivative. Okay. F of z is the antiderivative. So the derivative is f of z of t. Now let us look at this integration over a simple contour. between 2 points f of z dz. Okay. In terms of t, okay, because t extends from a to b, this looks like f of z of t, z dash of t dt. Okay. But this part okay, is the same as that part. Okay, so what happens now? I have integral a to b, okay, d by dt of f of z of t dt. Okay, this part here is equal to that, which is equal to this, which is equal to this. Okay, so I have replaced this by d dt f of z of t dt. So this goes away. So now we have the integral value given by f of z of b minus f of z of a. Okay. Thus the integral is independent of the path, is independent of the path. Okay, the path does not come into the picture, it is just a function difference of the endpoints. Okay, there is no path mentioned over here. Why? Because it has an antiderivative. Okay, so assuming first statement is true, the second statement turned out to be true. Okay, and finally, and if the second statement is true, and then we say if a is equal to b, a happens to be equal to b, then the integral is 0. Obviously the value is 0, integral value of the integral is 0. Okay, which is statement 3. Okay, now what we say here is we assumed 1 to be true, showed that 2 is true. Assuming or proving 2 to be true, 3 is true. Okay, but assuming 3 to be true, 1 is true is a bit involved. Okay, so I will not go into it, we will accept that. Okay, so that is our first theorem. So what we will do now is, for today we will close over here, okay, and we will explore the implications of this theorem in the next class. Okay, so see you next class. Thank you.